Welcome back to G Fun Facts Online. Today we are not looking up at the stars, but rather looking into the silicon brains that are watching them for us. The year is 2026, and it marks a specific, pivotal turning point in the human quest to answer our oldest question, are we alone? When we think of astrobiology, we usually picture the hardware like the James Webb Space Telescope or massive radio dishes in the desert. And while those giants are continuing to peer deeper into the cosmos, the most profound revolution in the search for life is not happening on a launch pad or a mountaintop. It is happening in server farms. We are seeing the rise of a new class of artificial intelligence known as foundation models, or FMs, and they are fundamentally reshaping how we search for life beyond Earth. To understand why this is happening now, we have to look at the history of the field. For decades, astrobiology was defined by data scarcity. We had exactly one data point for life, which is Earth, and surrounded by a universe of silence. But today, in 2026, we face the exact opposite problem. We are drowning in a deluge of data so complex and voluminous that human cognition alone can no longer parse it. We have spectral fingerprints of distant exoplanet atmospheres and terabytes of radio signals filtering through the Allen Telescope Array. The sheer scale of information requires a new kind of observer. This is the era of the silicon astrobiologist. These systems are multimodal, pre-trained, and capable of synthesizing knowledge across physics, chemistry, and biology of 1,000 worlds simultaneously. Let's break down this paradigm shift. We need to distinguish between the traditional machine learning of the early 2020s and the foundation models of 2025 and 2026. Traditional machine learning in astrobiology was often task-specific. You would have a model trained solely to detect craters on Mars. That model was brilliant at finding craters, but if you showed it a biosignature in a gas plume, it wouldn't know what to do. It was a specialist. Foundation models are different. They are trained on vast, diverse datasets, ranging from millions of scientific papers to petabytes of spectral data and planetary imagery. These models build a generalized understanding of the rules of nature. They can transfer learning from one domain to another. A model that understands the chemical grammar of terrestrial geology can, with minimal fine-tuning, learn to distinguish between a biological methane signature and a volcanic one on a distant world like K2-18b. This watershed moment really arrived in February 2025, when NASA Ames Research Center and the SETI Institute hosted the inaugural Foundation Models for Astrobiology workshop. The consensus from that gathering, which was solidified by the release of the Paper 1 white paper in late 2025, was clear. The future of life detection is AI-driven, multimodal, and autonomous. Now let's look at the specific tools making this happen. Astrobiology is inherently interdisciplinary. To evaluate a single potential biosignature, a researcher must synthesize knowledge from stellar astrophysics, planetary science, geology, and biology. No single human expert holds deep expertise in all these fields. This is where text-centric foundation models like INDUS and the proposed AB chat have become indispensable. These are built upon architectures similar to the commercial large language models we saw in the early 2020s, but they are trained on curated scientific corpora, including NASA technical reports, ArXiv preprints, and peer-reviewed journals. INDUS, which was developed largely by NASA researchers, has demonstrated an uncanny ability to connect the dots. In recent trials, when fed conflicting papers on the phosphine detection in Venus' atmosphere, INDUS was able to highlight subtle discrepancies in the calibration methods of different instruments. This was a nuance that had escaped human meta-analysis for months. Then we have AB chat, a concept gaining traction in 2026. This takes it a step further. It is designed not just to retrieve information, but to generate hypotheses. By ingesting the entire corpus of prebiotic chemistry literature, AB chat can suggest novel reaction pathways for the origin of life that have never been tested in a lab, effectively guiding the hands of experimentalists toward high-probability discoveries. But text is just one part of the equation. While text models synthesize theory, the heavy lifting of detection falls to multimodal models capable of seeing and smelling the universe. One of the most exciting breakthroughs of late 2025 is LifeTracer, a machine learning framework designed to analyze mass spectrometry data. In the past, distinguishing between complex organic molecules created by life, or biotic samples, and those created by space chemistry, or abiotic samples, was a slow, manual process prone to debate. LifeTracer changes the game. It was trained on thousands of samples from carbonaceous meteorites to terrestrial fossils, and it has learned the subtle chemical texture of life. In blind tests, LifeTracer achieved over 87% accuracy in distinguishing meteoritic organic sludge from biological samples. It identified that abiotic samples, formed in the vacuum of space, tend to contain compounds with higher volatility and specific retention times that biotic samples lack. This tool is now being integrated into the analysis pipelines for future sample return missions, potentially acting as the first line of defense in identifying Martian biosignatures. Simultaneously, we have models like Morpheus and ExoGAN revolutionizing exoplanet research. Morpheus was originally an image classifier for galaxies, but it has been upgraded to handle the deep infrared data from the James Webb Space Telescope. Meanwhile, ExoGAN, which is a generative adversarial network, is used to simulate millions of potential exoplanet atmospheres. By generating synthetic spectra of living and dead worlds under various stellar conditions, it provides the training data necessary to teach other AIs what to look for. This dreaming AI allows researchers to prepare for the detection of biosignatures that we have not yet observed in reality. Now, let's move to the edge of discovery. The search for extraterrestrial intelligence, or SETI, has always been a needle in a haystack problem. The haystack is the entire radio spectrum, and the needle is a transient signal that might last only milliseconds. In late 2025, the SETI Institute partnered with NVIDIA to deploy the IGX Thor platform at the Allen Telescope Array. This collaboration represents a move from post-processing to edge computing, deeply integrated into the telescope's hardware. Previously, terabytes of radio data were recorded and analyzed days or weeks later. If a transient signal like a fast radio burst or a potential technosignature occurred, it was often too late to verify it. The new AI-driven pipeline processes gigabits of data per second in real time. It uses a foundation model trained on all known forms of radio interference, such as satellites, cell phones, and radar, to filter out human noise instantly. This system effectively gives the telescope a reflex. If the AI detects an anomaly that defies known astrophysical or anthropogenic patterns, it can trigger immediate follow-up observations, locking the telescope onto the target before the signal fades. We are no longer just recording the sky, we are actively listening with an intelligent filter. However, despite this progress, the integration of foundation models into astrobiology faces a unique epistemological hurdle known as the n=1 problem. We only know of one instance of life, which is Earth. Training an AI to find life based solely on Earth data risks creating a homocentric bias. An AI trained on terrestrial biochemistry might stare right at a silicon-based organism or a plasma-based life form and classify it as a rock. Conversely, there is the risk of hallucinating life. Foundation models, particularly generative ones, are known to find patterns where none exist. In the high-stakes arena of life detection, a false positive could trigger a premature announcement of alien life, devastating the field's credibility. To combat this, researchers are employing anomaly detection rather than simple classification. Instead of teaching the AI what life looks like, they teach it what physics looks like. The model learns the baseline of abiotic processes, such as how rocks erode, how gas clouds cool, and how stars shine. Anything that deviates significantly from this thermodynamic baseline is flagged as an oddball. This approach aligns with the agnostic biosignature framework. We aren't looking for DNA or chlorophyll. We are looking for complexity that entropy cannot explain. We are looking for the statistical shadow of intent. Looking forward, as we move into the latter half of the 2020s and into the 2030s, the role of foundation models will evolve from tools to partners. NASA's planning for the Habitable Worlds Observatory, the successor to JWST, already incorporates AI as a core component of the mission architecture. We are moving toward the concept of the autonomous scientist. These are spacecraft equipped with onboard foundation models capable of making real-time scientific decisions. Imagine a probe in the oceans of Europa. Communications with Earth take hours. If the probe sees a fleeting plume of hydrothermal vent fluid, it cannot wait for instructions. It must recognize the scientific value of the event, adjust its trajectory, and sample the plume, all on its own. In 2026, the foundation for this future is being poured. We are building the silicon brains that will one day ride atop our rockets. These models are not just processing data. They are expanding the definition of what is knowable. By synthesizing the scattered knowledge of humanity, they are preparing us to recognize the other, whenever and wherever we finally meet it. The search for life has transformed. It is no longer just a search for biology, it is a search for information. And in this new era, our most powerful telescope is the neural network. Thanks for listening to this deep dive on G Fun Facts Online.